Hello everyone. So in this video, we'll be discussing one-way ANOVA, or what we call one-way analysis of variance. So basically, one-way ANOVA is one-way analysis of variance is used to test the claim that three or more population means are equal. So last time we have been discussing or the comparison of two datas within the group. Now here in ANOVA we are testing if there's differences between three or more populations. We are testing if the means of those three populations are equal. So one way ANOVA is also used to compare three data coming from one group. This is an extension of the two independent samples of t-test. However, here in one way ANOVA, we'll be using f-test. So the one way is because this is called one way because each value is classified in exactly one way only. Examples include comparisons by gender, race, political party, color, and etc. So the conditions or assumptions in one way ANOVA will still apply the null hypothesis and the alternative hypothesis. So the data are randomly sampled. The variances of each sample are assumed equal. The residuals are normally distributed. So here is the hypothesis that we have. The same with the discussions with our previous discussions. We have the null hypothesis. It means that there are no difference between the mean of the first, second, and third populations. So the null hypothesis assumes that there are no differences between all the datas. The alternative hypothesis, on the other hand, is that it means that it has at least one of the means are different. So they don't all have to be different, just one of them. Hindi meaning na si mean 1 is not equal with mean 2. It's just that either one of them are not equal. Okay, so that is for the alternative hypothesis. So we have here an example. The statistics classroom is divided into 3 rows, the front, the middle, and the back. The instructor noticed that the further the students were from him, the more likely they were to miss class or use an instant messenger during class. He wanted to see if the students further away did worse on the exams. So, gusto lang i-test ng professor if kung yung students na nasa likod nakaupo is mas lower daw ba ang result sa exams. So here, first thing that we need to do is identify our hypothesis. First is we have the null hypothesis. The ANOVA doesn't test that one mean is less than another, only whether they're all equal or at least one is different. So here in ANOVA, again, hindi natin ina-identify kung ano yung differences between the three samples. We are just identifying if there's difference between the three samples. Hindi yung value talaga ng differences. Okay, so this is our null hypothesis, which assumes that all the means or of the populations are equal. So we have the mean of the front, the mean of the middle, and the mean of the back are equal. So here are the datas that we'll be needing in solving for the one-way ANOVA. So a random sample of the students in each row was taken. The score for those students on the second exam was recorded. So for the front, as you can see, it has higher results than the middle and the back. However, since we already know that the frontliners or the front seaters has the highest results. However, we just have to test the significance of these results using ANOVA. So this is the summary statistics for the grades for each row written in this table. So we have the sample size is 7. For the front, for the middle, it's 9. And for the back, it's 8. For the mean, this is just the summation divided by 2 of the data that we have, the standard deviation and the variance. So here, first, the second step the first step was to identify the hypothesis. The second step is to complete this table. So we have here the data for the front, middle, and back. So we just have to find the square of this one. So square of 82, that is 6724. So you just have to write here in our table. And then all the squares of this one, you have to write it on the table. So after we have solved for the squared of the front, middle, and the back, we have to find the summation or the total of the front, the square of this one, the summation of all the datas basically. So the summation of the front of this one, or summation of x for this one, is you just have to add all of this together. So that is 530. For this one as well, that is the summation of x squared. So that is equivalent to 41994. This one, we have summation of x sub 2, that is 604. Summation of x squared sub 2, that is 41494. This one, summation of x sub 3, that is equivalent to 428. Summation of x sub 3 squared basically is equivalent to 23460. Okay, so that is our summation. Now for the front, middle, and back, we have to find the mean of this one. So let's have 75.71. This one, we have 67.11. And for this one, we have 53.5. So these are the data that we'll be needing later on in order for us to solve for the tables or the data for the ANOVA. So here are the other data that we'll be needing. So we have to find our K, our N, capital letter N, summation of X, our G, and our SS. So K here is the number of treatment conditions or the number of groups. So how many groups do we have? That is 3. So meaning to say our K is equivalent to 3. Now for the N, number of scores in each treatment. So the number of scores, since we have different data or number of datas here for the front, middle, and back, so meaning to say we also have 3 different n's. We have n sub 1, that is equivalent to 1, 2, 3, 4, 5, 6, 7. 7 datas. For n sub 2, we have 9. For n sub 3, we have 8. So these are the number of samples. So we have 2, 4, 6, 8, 9, 2, 4, 6, 8. So those are the n's. Now capital letter N is the total number of scores. So meaning to say we have to total all of this together. So that is our capital letter N, and that is equivalent to 24 samples. Summation of X, we have here different summations of our x's, the 530, 604, and 428. Now for the G, this is actually grand total. If this is the total, this is the grand total or the sum of all total in the study. So if our summation of x's are 530, 604, and 428, our grand total is, or the G is equivalent to 1562. Again, that is just the total of all the summations that we have. And for the SS, since we have different values or different number of data considered, so we also have to solve for each of this. So for the SS sub 1, our summation of x squared is, from the data, from the table, summation of x squared is 41,994. So meaning to say we have 41,994 here minus the summation of x. So the summation of x quantity squared, that is 530. So that is 530 squared all over the number of data for n sub 1, that is 7. So our SS sub 1 is 1865. Point 43. Okay, so for SS sub 2, we have a summation of x for this case, x squared for this case is 41,494. Subtracted by the quantity squared of 604 squared all over our n sub 2, which is 9. So basically, this is equivalent to 958.89. Now for SS sub 3, that is equivalent to 23,460 minus summation of x 428 squared all over number of samples, so that is 8. So that is equivalent to 562. So these are our SS sub 1, or sum of squares of data 1, sum of squares of 2, sum of squares of 3. Now after this, after we got the values that we'll be needing later, so we have to solve now for the ANOVA table. But first, before we solve for the ANOVA table, we have to understand what are the contents, or what are the meaning of the contents in the ANOVA table. So we have here the variation. Variation is the sum of the squares of the deviations between a value and the mean of the value. Sum of squares is abbreviated by SS. So meaning to say here, this is sum of squares, and often followed by a variable in parentheses such as SSB or SS between, or SSW or SS within. So we know which sum of squares we are talking about. So here, since all the values are not identical, so there is some variation in the data. This is called the total variation. This is denoted by SS total. For the total sum of squares, that is variation. Sum of squares is another name for variation. So here, are all the sample means identical? So there is some variation between the groups, and this is called the between group variation. So that is denoted as SSB, or sometimes sum of squares between treatments. This is called the between group variation. So earlier, that was within, SSW is within group variation, sometimes called the variation due to the factor. It is denoted SSB for sum of squares variation between the groups. So here is our ANOVA table. So this is the last step actually. We have to complete the ANOVA table. So we have here the between treatments, this is SSB. Within treatments, this is SSW and the total. So we have to find the SS of the between, or SSB. We also need to find the SSW and our SS total. So in finding this one, we can find first the total going up. So for the SS total, that is equivalent to the summation of x squared minus grand total all over capital letter N. So this is already the total of all the samples that we have. So if you would summate, or if you would add all of the summations here, if you would add this one, the summation of x squared, that would be equivalent to, that is equivalent to 106,948. And then if you can recall, our G earlier is equivalent to 1562, and our N is 24. So that is 1,562 squared all over 24. So this is the formula for the SS total, for the sum of squares total. So that is equivalent to 5287.83. So you can write it here, 5287.83. Now for the SS within, or SSW, that is equivalent to the summation of SS, or the summation of SS inside the treatment. So inside the treatment, these are, so basically this is just the summation of all the SS that we got earlier. This one, we have 1865, this one, summation of the 3 SS that we got. So that is basically equivalent to 3,386.32. So that is what we are going to write here, 3,386.32. Next is, in order for us to get the SSB, that is equivalent to the SS total minus our SSW. So here, SS total is 5287.83 minus our SSW, which is 3,386.32. So meaning to say our between treatment, or the SSB, is equivalent to 1901.51. You will also know if your answer is correct for the SSB and SSW if you add them together, that is equivalent to the total. Okay, so that is for the SS. Now, we need to find also the degrees of freedom here. So for the degrees of freedom, we have 3 different equations or formula. We have for the total, the within, and the between. So for the DF total, that is equivalent to capital letter N minus 1, or 24 minus 1, that is 23. So our degrees of freedom here is 23. Now for the DF of within, or W, that is N minus K. If you can recall earlier, our K is 3 because we have 3 groups. So we have 24 minus 3, that is 21. So this answer here is 21. Now for the degrees of freedom for between, we have K minus 1. Our K is 3 minus 1, so that is 2. So basically, our degrees of freedom for the between is 2. So next one, we have to find our MS. So we cannot find the block one. We just have to find this one. So MS, for MS between, for the MSB, that is just SSB divided by our DF. So basically, SSB is 1901.51 divided by 2. So that is 950.76. For the MSW, we have SSW divided by DF. So this one divided by this is equivalent to 161.25. Okay, so that is again 3,386.32 divided by 21. So that is 161.25. Now for the F, that is just division of 950, or the MSB divided by MSW. So our calculated F is MSB divided by MSW. So basically 950.76 divided by 161.25. So that is equivalent to 5.9. Next one is the table F or tabular F that is based on the table that we have for the F test. Okay, so we need to find our table or tabular F. So from the table we have here, in order for us to identify what is our table F, we have to identify our degrees of freedom for the between and degrees of freedom for the within. So this is our numerator, this is the denominator. So from the table, in order for you to check the table F, so that is our numerator. This one is the numerator. This one on this side is the denominator. So since our numerator earlier is 2 and our denominator is 21, so meaning to say our tabular F is 3.47. So that is 3.47 here. So in order for us to check if we would reject or accept the null hypothesis, is that if the value for our calculated F is greater than the value of our table F, we will be rejecting our null hypothesis. Again, if this is greater than this one, we would be rejecting our null hypothesis. So that means that there is a significant difference between the three datas that we have. Okay, so I hope you learned something from this video. This is already the answer for the example earlier. Thank you everyone, and God bless us all.